Making life multi-planetary will extend the light of human consciousness. It is physically impossible to make a rocket that can fly from Earth to Mars and back without refueling on Mars. So the rocket propellant production plant on Mars can really be thought of as the second most important piece of infrastructure you need to build a city on Mars and the core engine that makes the city on Mars run. What Starpath is building is the machines that make that possible and make it possible at unit economics that make the cost of a round trip to Mars a price that a middle-class American can afford.
This is Saurav Shroff, and he is the co-founder and CEO of Starpath. And Starpath is basically trying to make life multi-planetary, or was founded to make life multi-planetary. Do you want to just start off with what are the inputs to basically making a self-sustaining city on Mars?
Yeah. Well, first of all, thanks for coming. Totally. So there's basically two machines that you want to make to start to make life multi-planetary on Mars. The first machine is a fully and rapidly reusable rocket. So this is a rocket that can fly and refly like an airplane, where the primary expense in operating the rocket is fuel, and the secondary expense is refurbishment or maintenance or whatever. But the primary expense is not building the rocket. Mm-hmm. This is important because if you don't make a fully and rapidly reusable rocket, the unit economics of transporting cargo and crew to the surface of Mars will be far too expensive. The second machine that you need to make doesn't necessarily meet the eye. It's not necessarily as obvious. It's a rocket propellant production plant on Mars. And this is because it is physically impossible to make a rocket that can fly from Earth to Mars and back without refueling on Mars. Now, if you make a rocket that can fly to Mars but can't get back, the journey is both costly and morbid. So nobody will go. And so you need to make a rocket propellant production plant on Mars. And it turns out that if you sketch out a city on Mars really in any way, if you imagine it with a few people, a lot of people, a short stay time, a long stay time, whatever, that city will spend 90 to 95% of its power producing rocket propellant. So the rocket propellant production plant on Mars can really be thought of as the second most important piece of infrastructure you need to build a city on Mars and the core engine that makes the city on Mars run.
So can you basically go into the math on how the 95% works out?
Yeah, it's super shocking fact up front. But basically, so first of all, the question is how do you make rocket propellant? For a vehicle like Starship, the vehicle consumes oxygen and methane. In a rocket engine, the oxygen and methane burn to produce, obviously, energy in the form of heat and CO2 and water. The rocket propellant production plant on Mars ingests water, which is in the Martian crust, and CO2, which makes up the majority of the Martian atmosphere, and adds power via solar energy to turn that CO2 and water back into methane and oxygen. So the rocket propellant production plant, in simple terms, can be thought of as the opposite of a rocket engine. A rocket engine takes
an inverse rocket engine.
It's an inverse rocket engine. And so a rocket engine is, approximately speaking, the most energetic device, roughly, short of a nuclear fusion reactor or like a grenade, but even a grenade is pretty low energy compared to, 33 rocket engines on the bottom of a rocket. So rocket engine is the most roughly energetic thing that the human species has ever made. And what we need to do is go to Mars and build a machine that does the opposite. So now you can start to picture okay, why is it the case that all the energy that 95% of the energy we produce on Mars will be spent on rocket propellant production? Well, it's because, you're undoing the most energetic thing that humans really do ever. And so what Starpath is building is the machines that make that possible and make it possible at unit economics that make the cost of a round trip to Mars a price that a middle-class American can afford.
So basically, how does the technology work of taking this water and everything from the surface of Mars and then the CO2 in the atmosphere and turn it into rocket fuel? How does that work?
Yeah, it's so at a chemistry level, the production of rocket fuel on Mars is extremely simple. It's high school level chemistry. What you do, and I'll talk about the chemistry first and then the implementation with robots after. What you do is you take dirt out of the ground that has water in it. You heat up the dirt to extract the water as pure water with obviously no dirt in it. You then take the water and you split it into oxygen and hydrogen, which are, of course, water. The water molecule is made of oxygen and hydrogen atoms. So you split it into oxygen and hydrogen, which is the most energetic part of the process. Rocket fuel, just to recap here, is oxygen and methane. So we now have one component of a rocket fuel. For simplicity, we'll call it half, although it's actually 80%. And to produce the methane component, which is the other 20%, you react the product hydrogen from splitting water with the CO2 that is abundant in the Martian atmosphere. to produce methane. And that reaction actually releases a little bit of energy, which feeds back into the process. So from a chemistry standpoint, it's super simple. In fact, high schoolers will remember that in their high school chemistry class, they probably did something to the tune of like putting a nail in a bucket of water and like seeing some bubbles form. That is just extremely low efficiency and high unit cost water electrolysis. So from chemistry standpoint, it's like a total walk in the park. And this is actually a part of the reason why methane and oxygen were selected as the propellants for Starship. And we hope that trend continues if more companies develop similar vehicles. From a robotic implementation standpoint, that process breaks down into 3 machines in no particular order. One machine generates power. In the early days, that'll be done with solar energy. And in the long term, it'll be done with nuclear. The second machine is a machine that ingests dirt that's mined and does the chemical reaction I just described. And then the third machine is a mobile robot that drives around the surface of Mars and digs up huge amounts of dirt as a raw feedstock for this process. And we build all 3 of those machines, and we're designing them to be produced at massive scale. So for context, we built the lowest cost, fastest driving rate, and highest performance Moon over Mars rover ever made. And in a few years' time, we'll build a factory that can make thousands of them every year.
Previously, how much does a Mars rover cost for like NASA to build?
It's a good question. There are a lot of NASA rovers that have been built in the past.
Yeah.
None of them have been made for under $100 million, and many of them have been made for over $500 million. Importantly,
does that include the cost to launch them to Mars?
No, that number does not include the cost to launch to Mars.
Research.
Yeah, and for context, I'm referencing both rovers that NASA has made for the Moon and for Mars. So NASA has built a ton of what I would call really impressive science machines. So machines that are optimized to do like 50 disjoint experiments on, water concentration, mineral type, soil type, various questions that scientists around the world have been asking. But what NASA has never done is ask themselves, okay, how cheap can I get the unit cost of water on Mars? And subsequently, how cheap can I get the unit cost of propellant? This question is only relevant when your objective is to make life multiplanetary. And it's a totally irrelevant question for the objectives that NASA has, in my opinion, admirably chased over the past, called 3 decades, which is to advance science. So in the past, just to answer your question directly, the number has been hundreds of millions of dollars to build rovers, where if NASA were to build a second or third version of that rover, it would still cost them tens of millions of dollars. At Starpath, we're building rovers for the low hundreds of thousands of dollars. So we're talking about an over 100x cost reduction. And that's driven by vertical integration of all of the components that make the rover challenging to manufacture, or I should say costly to manufacture, and a design that's designed around mass production.
Yeah, and I know you mentioned that you basically set out to kind of build the propellant production, and then suddenly you ran into the situation where the cost of solar panels, which we're looking at and like we have in the background here, they're just like orders of magnitude more than you really need them to be. How did you decide to basically go from just propellant production to now building solar panels?
Yeah.
What was that process?
Yeah. So for context, we didn't really decide to go from just building propellant production to building solar panels. The early days of Mars will be solar powered. So we started by building massive deployable structures that could get you huge amounts of solar power production on the surface of the Moon and on the surface of Mars. And what we initially did was we built the structures, and then we went to try and buy the solar cells from the existing marketplace of vendors that sell solar cells and solar panels and solar modules, mostly to satellite companies. And what we found was that the unit economics, and you're not going to believe me, but I promise you I'm not lying, the unit economics of buying just the solar panels, so the quotes we got from vendors for just the solar panels, which mind you, we have to build deployable solar panels, rovers to mine dirt, and plants to process the dirt into rocket propellant. So for just the solar panels, we're 10 to 20 times more than what we want to spend on the entire system. So we wanted to spend, on a per watt basis, which I'll explain, what I mean by on a per watt basis later, like $10 to $20 per watt. And we were getting quotes between $100 and $400 per watt for just the solar panels. And so what we did was, like I said earlier, we vertically integrated the production of that product for our own purposes so that we could build a base on the Moon and a city on Mars. It would just be completely financially impossible to do it by buying solar panels from the existing marketplace of vendors. And then after doing that, and we didn't plan to do this at all, but after doing that, we realized like, okay, well, we have extremely valuable product on hand. All of the satellite companies are trying to scale their operations. The supply chain can't keep up in production rate and definitely can't keep up in cost. So we've now entered that marketplace as well. So now we sell solar panels to satellite companies for about 1/10 the price that you can get from the vendors that we ourselves tried to buy from and failed to buy from.
Yeah, and so I want to try to understand, why did previous solar panels cost so much and solar cells cost so much?
It's a tough question to answer because I don't work at the companies that make those products. But roughly speaking, the satellite supply chain, meaning the supply chain for all components that go into satellites, are based on, what I would call extremely low volumes and high unit costs. So they're sort of based on the economy of yesterday, where, okay, maybe a satellite company is building a satellite for NASA or for JPL or for Viasat or something, where there's like 3 satellite launches a decade. And when there's 3 satellite launches a decade, and you're building a business that supplies the company that makes, a satellite every 1,000 days, instead of a company that makes a satellite like every 1,000 minutes.
This wasn't designed for scaled production.
Yeah, it wasn't designed for scale production. And the incentives are completely misaligned, where, if you tell, a customer that's buying, 50 kilowatts of panels every 2 years, like, hey, I'll charge you 10x for 10% more performance, that looks like a good deal. But the economy is shifting, obviously, towards scale and lower unit cost. And the supply chain really hasn't changed much since, the early 2000s. So, the businesses that exist today are supplying companies of yesterday. And, Starpath, while we didn't necessarily intend to be in the business of supplying satellites, we're really looking at supplying the satellites of tomorrow, where companies want to build, constellations of thousands of satellites that service, really big markets like telecom and Earth observation and stuff like that.
I know that you were thinking about basically trying to also build a similar propellant production facility on the moon. But then I think it's kind of like moved and shifted away from that. Why did that happen?
So I would say, yeah, you're kind of right, not entirely right. The products that we build, the rover and the plant, so that the machine that digs dirt and the machine that processes the dirt and turns it into rocket propellant, are designed for the moon. So they will work on the moon. And there's a lot of interest, particularly from government customers, to build a base on the moon. And we think that that's going to happen. That being said, in the long term, so 10 years from now, 8 years from now, 20 years from now, if you ask the question like, okay, out of the 2 planets, or I guess moon's not a planet, but for simplicity, the 2 planets, moon and Mars, which one's more interesting? Mars is a fundamentally more interesting planet because it has organics. So it has carbon, hydrogen, nitrogen, oxygen. And with organic compounds, you can make a completely self-sustaining city on Mars. There's nothing that humans consume that you could point to on Mars and say like, okay, that's not possible to make. You can make obviously rocket propellants, obviously electricity, obviously water for drinking, obviously oxygen for breathing. Okay, that's the majority. You could also make Tylenol. You could also make computer chips. You could make, vitamin C. You could make, bread. And it wouldn't be necessarily trivial to make those things, but you could. So from a standpoint of like what planet from first principles physics is more interesting to go build a huge base on, it's definitely Mars. Mars is a world where, in 100 years, we could turn it into a planet that looks not quite like Earth, but, way more like Earth than it does today. And for the moon, the same story really can't be told. There's no world where there's liquid oceans on the moon. There's no world where there's an atmosphere on the moon. There's no world where you have Tylenol production on the moon. And so from long-term standpoint, that's true. And at this point,
is it just because the moon just doesn't have the same like resource composition?
Exactly. So the moon doesn't have access to the same organic compounds that Mars does. So if you wanted to make something like bread, you would find that from an elemental standpoint, the actual elements that go into making bread, some of them aren't present in large quantities on the moon. So even if you take out the fact that like, okay, there's barely any water on the moon, there's no atmosphere, the nights are 14 days, the days are 14 days, and you just look at the fact like, okay, theoretically with infinitely capable technology, could I make this a planet that's livable? The answer is no. But with Mars, the answer is absolutely yes. It's just challenging to make that technology, and we're up for the challenge. And now that sort of like if you look at like, okay, like what entities in the world define where humans are going to go? Obviously, a company like Starpath will be, one of those major players in a few years. But right now, there's basically 2 major entities, and it's NASA and it's SpaceX. And SpaceX has been very clear publicly about their objectives. I mean, SpaceX is building a rocket that can go to the moon and Mars. But if you look at their publicly They're publicly talked about plans. The overwhelming majority of the rockets that they're building are Mars bound. Right now, SpaceX is building a factory that can make tens of Starships per year. Soon it will be hundreds of Starships per year, and the fleet of Starships will be 1,000 plus. Both low Earth orbit and the moon are very close. So there's no reason to have a fleet of 1,000 Starships unless you're sending them to Mars. In fact, just 2 Starships could service the entire low Earth orbit market for satellites, and something like 5 Starships could service, effectively infinite volume of cargo to the surface of the moon. The only reason why SpaceX is building 1,000 Starships or a fleet of 1,000 Starships, which they've talked about publicly, is because the round trip journey to Mars and back takes about 4 years. And so if you want to do, 1 million tons of cargo to the surface of Mars, you have to have a big fleet because, you can't refly the fleet every day or every 2 days or every 5 days like you can with low Earth orbit and the moon.
I also find it kind of interesting that it's honestly, like, at least short term, like way more efficient to just basically scale the production of Starships on Earth instead of trying to even get the Starships back from Mars in the first place. Because it's just so much easier to put up a production facility here.
Yeah. So in the early days, and SpaceX has now talked about this publicly, although, I'm not a spokesperson for SpaceX, so to take this with a grain of salt, in the early days, they will not be bringing Starships back from Mars. They're one-way trips, and they're primarily one-way trips for the reason that building the infrastructure on Mars is extremely, extremely challenging to enable Starships to fly back home, and that's why we exist. So SpaceX will tell you that they're going to fly Starships back from Mars. I don't know what date they're talking about these days. Our goal is to make that possible at least 4 years sooner than they're expecting.
So how do you do that?
Yeah, it's a great question. So, Starpath's primary technology is our primary objective is to make it possible to fly Starships back from Mars to Earth by building propellant production plants on the surface of Mars. There are a few other technologies that it's like sort of like there's questionable, like whether you do or don't need them to fly back from Mars. Like, some people talk about the fact that like maybe you need a landing pad to launch from on the surface of Mars. That one's sort of like TBD. I think the answer is like probably yes. And, we may be able to solve that at some point. We haven't thought about it, super in depth because it is not really the bulk of the challenge. The bulk of the challenge is like, okay, my rocket on Mars needs 2,000 tons of propellant. The current production rate of propellant on Mars is squarely 0 grams. It's not even 0 kilograms, 0 grams. Okay. So you have to get from 0 grams to, 2 billion grams. And you have to do it in a short enough time where the propellant that you produce on Mars doesn't boil off. So you have to make that 2,000 tons in just a matter of, a few days or a few weeks. So that's like really the bulk of the challenge. And that's what the products that we build solve. And so, we won't talk too loudly about the dates we think that'll happen, but what we do say is it's a lot sooner than you think.
Why is it important to you to basically make life multiplanetary and be a part of that journey?
Yeah, I think this is like the most important question. And, there's two angles to think about it. Like the first is philosophical, which we'll go down. And the second is business, which I think is like, it's important, but it's far less important than the philosophical angle. The philosophical angle is fairly straightforward. It's just making life multiplanetary will extend the light of human consciousness. Humans are like, or Earth is like a ping pong ball in an Olympic-sized swimming pool, and life is like a thin, like almost impossible to see layer on the outside of that ping pong ball. And to us, the Earth looks big because we ourselves are small. But what we don't understand is that human life is fragile. And there are tons of things, some in our control and some out of our control, that sort of threaten the long-term survivability of humans on Earth. And I'm an optimist. Like I really hope that, all of the things, all of the technologies that we make that threaten the life of humans, don't get used, ideally don't get made. But to deny that there's any risk there is like totally
it's like
ignorant.
being a ostrich and sticking your head in the sand.
Yeah, it's like okay, your ping pong ball life is like like a nanometer thick coating or like a 5 nanometer thick coating on the outside of this ping pong ball, and you have like a bomb that can blow up the ping pong ball, and you're like, oh, it's like, is this a good idea? Like, should I have multiple ping pong balls? And the answer is like absolute yes. Today, if you try to project like, okay, what is the expected lifespan of humans? I think you could, if you're really generous, describe it as being in the tens of thousands of years. Like, okay, we've got this technology, nuclear weapons, bioweapons, et cetera. We hope that nobody ever uses them. Okay, what's the expected time span over which somebody does make a mistake? I would love to be an optimist and say that that's like 50,000 years. Okay, so like whatever, 1,000 plus generations. Keep in mind, we've only had these technologies for like 3 generations. So like I'm like saying, I think we can survive the creation of nuclear weapons for 100 times more time than they've existed. But if you make life multiplanetary, particularly if you start with Mars and then you expand to like some of the other moons in the solar system, you can easily project that number. Like, okay, what's the expected lifespan of humanity to be in the millions of years? And then once you're in the millions of years, now you can project all sorts of new technologies that enable humans to do things like light speed travel. Maybe we can make Dyson spheres. And so if your objective is to have a good time on Earth, then yeah, absolutely, Mars is not for you. But if your objective is to make humans the greatest species that have ever been, Mars is a great first step to 1, increase our longevity, and 2, increase our skill in the ability to proliferate across the galaxy. So the philosophical angle is really going to Mars is a first step in extending the light of human consciousness. We're a very small light in a very big place. And to make that light brighter, Mars is definitely our first step. It's almost like God wants us to do it. The business angle is like...
Gave us a side quest.
Yeah, he gave us a side quest. He's like, here's a planet. It's like kind of shitty.
Fixer-upper.
It's a fixer-upper. It's good enough that you could go there if you were like good at camping. It's like camping extreme edition. And if you're really good at camping, you can make it like a paradise. You can have liquid oceans and, which, okay, in my definition of paradise is like liquid ocean is a paradise. And
a little bit of an atmosphere.
You can have, it's got a pretty shitty atmosphere. You can make it a little less shitty.
Right.
You could nuke the poles, which, okay, a lot of people talk about. It's not that good of an idea, but you can make the atmosphere a little bit better. And then from the business side, it's like, okay, well, Mars offers something that can't be sold on Earth, which is the greatest adventure that humans have ever done, period. Like there is no, like people in the past, I mean, the original, like the origin of the term venture capital is capital that was given to people to go on ventures. Or
adventures,
right? Yeah. Venture capital was initially created so that, like a courageous sailor could go buy a boat and try to like sail to an island and hopefully find like, I don't know, potatoes or something, or ore, and then bring it back to wherever you started from. And so, Mars is a place that allows us to sell the greatest adventure of all time to people who want to go. And our job is just to make it so that the price of going to Mars is lower than the price that people want to pay for this incredible adventure.
So you're basically thinking about it from the perspective of, okay, SpaceX is going to solve the transportation to and from, and here's like some other angle where you can radically help that mission, but it's not directly the transport part.
Yeah, absolutely. So we're definitely not in the business of making rockets.
Yeah.
And we don't find ourselves to be competitive with companies that make rockets whatsoever. All we're saying is that if you want Mars to be an explosive, proliferative business, which is a prerequisite for it being a proliferative thing that humans do at all, right? We're not going to do a $1 trillion charity project to go to Mars. It's just like, maybe it'll happen, but not practically, right? It won't happen. And so,
but honestly, it wouldn't. I don't think the money would be spent well either if it was a massive charity project. You typically need some good incentives,
right? You need to have aligned incentives. It needs to be the case that people who want to go to Mars are paying, and the things that they want to build those things require you to make the city bigger and better. That's how you're going to get a big and good city on Mars that's self-sustaining, not like, a project where you like think about it and like theorize what would be great and try to do it. It's just like, there are no examples of that happening in history. So, from business angle, it's like, what can Mars sell? Well, what it can sell is extreme novelty, the greatest adventure of all time. And so if you want, no matter how good your rocket is, even if the rocket's free, there still has to be a thing on the other side of that rocket that somebody wants and wants to pay for.
So let's talk about like when you first started the company, how were you thinking about the like kind of critical path to getting to here and then also to just like making the thing happen?
Yeah. So actually when we first started the company, we had like tons of wrong input assumptions.
What were those?
Yeah, dude, we thought that Starship was going to fly in 2024 to Mars, which at the time, okay, looked like it
was on Elon
plausible.
time.
Yeah. I mean, like we were on Elon time and, I'm always an optimist. So, I didn't want to say that we think Starship's going to fly in 26 when SpaceX thought it was going to fly in 24. We're like, okay, 24. And it really looked like it. So that was one of the wrong assumptions we made. And the dates are a little bit different, although I still think Starship's like one of the more incredible programs in the world. I don't think that's an unpopular opinion. Our path to success was simple. It was, build the equipment that will make a city on Mars possible. And then wherever possible, take that equipment and deploy it on the moon, both to earn revenue, which is a more complicated question that I can get into later, and also to test it. And so more or less, that plan is the same. So I mentioned earlier, the products we build today, are designed for use on the moon. And that is because the first missions of our equipment to space will be to the moon, even if we think that in the long term, the vast majority of deployments will be on the surface of Mars. And so that's what we've done. I mean, we've built, like I mentioned earlier, the lowest cost moon rover ever made. We're preparing that for a flight. I'm not at liberty to share dates, but
soon.
And it'll be pretty epic. It's going to have, I don't want to spoil stuff that we haven't talked about yet, but it's going to be pretty amazing. And so once we have the vast majority of the technology deployed on the moon at some, call it small to medium scale, and by small to medium scale I mean huge scale in the context of things that have been deployed in the past, but small scale in the context of things that we'll deploy in the future, then we'll turn to Mars. And so we'll start mass producing the goods, rover, plant, solar farm, etc., for the surface of Mars. And when the time comes, we'll send a huge amount of payload to the surface of Mars that's capable of generating megawatts of power and thousands of tons of propellant.
So for the rover, what was the process for iterating on that and making it something that actually functions, and what was the actual end goal that you were going after with that? Especially because it's going to start going on the moon first. Yeah.
So rover development at Starpath, I think is like a first of its kind program, where instead of taking a complicated set of requirements, and trying to build a design that works for every one of those requirements, where maybe we've never done it before, so we sort of have to take a safe bet on every single one and spend a ton of money. We said, okay, let's just make a rover in the shortest possible amount of time. So the rover behind you, the one that's white and gold, we call Rover 10. And that's because we've made 9 rovers before it. The first one was literally made out of 80/20, which is commodity aluminum beam that you can buy from Home Depot, McMaster Car, wherever. And we built it in 3 weeks.
So you guys just went to Home Depot, bought some parts, and then...
Bingo. We went to Home Depot, we bought some parts, and we were like, okay, let's try to make, out of all these requirements, it needs to survive cold temperature, this, that, whatever. Let's ignore them all and start with the simplest set of requirements. Let's make something with wheels that moves. And believe it or not, Rover 1, to say that it moved would be true. To say that it moved well would be a stretch.
A little bit of a stretch.
Right, exactly. And Rover 1 took us literally 3 weeks to build. So we built it in a garage, basically in San Francisco, where the company started. We spent 3 weeks and probably $10,000 or less, I don't actually remember, on Rover 1. Rover 1 pretty much didn't work. We looked at it and we made a document called Problems on Rover 1 to be fixed on Rover 2. And it was a long list. We then said, okay, how quickly do we think we can make a Rover 2 that then actually fixes all these problems? And it turned out the answer to that question was something like 5 weeks. Okay, great. So now we have Rover 2. Rover 2, I'm now remembering, also made out of 80/20. Now it has some sort of custom sheet metal steel parts. It kind of drives. It's got a unique suspension. We learned a thing or two about the balance of the wheels.
How much did the cost of Rover 1 versus Rover 2? What was the difference?
Okay.
Was it a few $100 or a few $1,000s?
Rovers 1 through 5 were all built in under 8 weeks each, and all cost under $15,000. I mean, they're just we're just going as fast as we possibly can to understand, okay, what shape works? What material works? If I put the wheel outside of the axis of steering, does the wheel bend inwards? Does the wheel bend outwards? And we were basically just on an exercise, how quickly can we learn about what it takes to make a robot and where the actual limits are. Then with Rover 7 onwards, we started actually trying to build a machine that would work in space. So Rovers 8, 9, and 10 were all progressive steps in terms of Rover 8 worked in a vacuum, kind of. It probably didn't actually, but it sort of theoretically might have. Rover 9 also sort of a little bit better, worked in a vacuum, was sealed against dust. And now Rover 10 is our first rover that actually came out of what in the industry is called a thermal vacuum test, which is sort of like the graduation exam for moon rover. So it's like a thermal vacuum test where you like put a robot in a big chamber. The chamber simulates the conditions of various planets. Our test was for the moon. And you evaluate whether or not, A, does it break? Okay, thank God, Rover 10 doesn't break. But also like, is our model of like how it behaves thermally, how it behaves mechanically correct?
Yeah.
And so from Rover 1 to 10, it's like 2.5 years or whatever, it cost us no more than, well, I don't know that we can share publicly. I'll say that it cost at least 100 times less, or at least 10 times less than you'd think. Now we have Rover 10.
Was it like less than $1 million for all of them or something?
Not quite, but you're not far off.
Okay.
It's like a few $1 million for all of them. And now Rover 10, within a few $1 million, is the lowest cost of production and the lowest cost of development rover to ever pass TVAC, to our knowledge.
And what is TVAC?
TVAC is thermal vacuum test. So it's like it's like what I was talking about a few minutes ago. It's a graduation exam for a rover. It's a big chamber, simulates the conditions of a planet. TVAC stands for thermal vacuum. And it's like the final test that you put a robot through to figure out like, okay, does it work? And now we're building Rover 11, which is even better than Rover 10 in a bunch of different ways. I could get into like the technical list. It would take forever. But it's better than Rover 10. It's easier to produce. It's more robust. It's faster, etc. And Rover 11 will be finished early next year.
And so for rovers 1 through 10, I know that you were testing them in like a thermal vacuum chamber. Were you also like going out and aren't they going to just be like collecting a bunch of basically dirt? And so are you like going out to a desert to, have them collect dirt? How did you test them?
Yeah, it's a great question. So actually right where you're sitting, if you look behind you, you can see a bunch of scuff marks in the concrete. That's because right here, there used to be a 25-ton pit of semi-cemented concrete. So it was like semi-soft concrete. We would drive the rover into the pit, mine stuff, like evaluate how well it mines stuff. Eventually we got rid of the pit because it was sort of like a safety hazard. Like, every time the rover mines stuff, it like releases huge clouds of dust that are like, I would say lifespan shortening to breathe in. So we removed it. And now we do sort of like more scientific testing now that we've got the mining portion down. For Rover 10, we actually put a slab of that same concrete in a thermal vacuum chamber. So it was like not just mining, but it was mining while super cold, while being like, while in a vacuum, basically under the simulated conditions of actually mining on the moon. And so, I mean, and oh my God, this is a crazy question. Back during the Rover 1 days, we had literally a sandbox in our office. Like people would come over and be like, oh, is this like the playpen for engineers? Like as a joke. It was not a playpen for engineers. No, it's so gross. I do not recommend a sand pit in your office. But we would use that to test like, okay, driving capability, mining capability, super, super crude. Like, okay, does this shape work? Does this shape not work? Like really, really basic stuff like that. But now we sort of elevated to the scientific level where we like calibrate the strength of the material, put it in a vacuum. It's arguably more boring nowadays, but you have to do the science to get it right.
So how do you get like the best simulated soil composition of Martian soil on Earth?
Yeah, I mean, this is like a super long question to answer. The short answer is you make some guesses and you just take the worst possible case. There's like, between 50 and 100 research papers on this, and they're all like kind of the same in that they're like, okay, here's our guess as to what it might be. This is like the range of values we expect, where the range is like, 1 on the bottom and like 75 on the top.
Well, they've taken like Martian soil samples, so we kind of know what it is, right?
Right. Yeah. So we know a little bit about Mars from NASA's missions to Mars, and we know that the Martian soil is at least probably softer than soil on the moon. And so really what we've done is we've taken like, okay, we've read all the literature. We know that there are like 700 possible configurations of dirt, and just like, okay, what's the worst for our equipment? The worst for our equipment is, if the dirt is what's called subangular, meaning that the actual pieces of dirt are sharp at a microscopic level, and that they're sort of like cemented and frozen solid. So what we do when we test is we just buy simulated subangular dirt, freeze it with liquid nitrogen with a calibrated amount of water in it to get it to be that super hard material. Now, all of our engineers think that in the real world, when we actually go to the moon and Mars, we're going to find that it's like
pretty chill,
way softer, and pretty chill, as you're saying. But the only right path forward from you can't engineer around a guess. You have to engineer around like, okay, the worst case is this. So We're going to build a machine that can handle that. And it's not so bad. Like mining equipment is, we mine harder and nastier stuff on Earth all day, every day. For like lithium mining, iron ore mining, everything. So it's not like there isn't knowledge base among the human civilization of like how you dig up hard dirt.
Let's run a hypothetical scenario. In a hypothetical world where SpaceX does not exist and the capability of like reusable rockets doesn't exist, would you be trying to build that? Is that
Would
something in your
I personally
wheelhouse?
be trying to build reusable rockets if SpaceX never existed?
Correct.
I think the real answer to that question, like I would love to say yes, like, oh yeah, I would do anything to make Mars happen. I think the real answer to that question is that like SpaceX is the reason why people believe that challenging things in aerospace are possible to do in the first place. Like if you take SpaceX out of the equation and you ask yourself like, what does the aerospace industry look like? It looks kind of like a lot of other industries where you sort of assume the innovation has dried up. Like it looks, I don't know much about oil and gas, but it looks like what I think of as oil and gas, which is like the same thing over and over, where the companies have probably done what can be done to make it more efficient already. And
it's kind of commoditized across every single competitor.
Right. I don't know much about oil and gas to be very clear, but that's what I think of when I think of oil and gas. And I think sans SpaceX, the aerospace industry looks almost the same. And so my real answer to your question is sort of a non-answer, which is I think sans SpaceX, you probably wouldn't even have, like you probably interview 5 aerospace companies a month. I don't think any of them would exist sans SpaceX, not just for the economic reason that like, oh, they wouldn't be able to launch their stuff into space for a price that they can afford, but also for the reason that like SpaceX and the things that they've done have made other people in the world think like, okay, if you put your mind to it and you hire the best talent and you cut down on fluff and you cut down on bureaucracy, that you can actually produce an outsized return in terms of technology developed per dollar. Like I won't name names, but like other companies are not the most confidence inspiring in. Like it's not like you look at some of the programs that you see in the rest of the industry and think to yourself, oh yeah, like if I copy that, I'm going to be able to change the world.
Right.
But if you just copy, Starlink, not for Starlink, but like, you make a Starlink for something else, low cost, high rate, serves a big market, you could see a world where a new technology like Reflect you're talking about changes the world.
What's been the biggest like technical hurdle or technical challenge so far?
There are a lot of sort of disjoint technical challenges. I would say the biggest, there's no particular biggest. My team will be mad at me if I like cite one thing that's the biggest. The thing that I would say is probably the biggest is actually a broader problem with the US, which is the access to low cost, high rate manufacturing. Particularly when you make real goods, the difficulty of making that good is sort of like a risk adjusted analysis of how good a thing is when you're designing it against how quickly and frequently you want to buy it. So like if you're designing, I'm just going to give you a simple example. If you're designing like a motor assembly for a robot, and this is fresh in my mind because last night I was watching an engineer design a motor assembly for a robot. If the motor assembly cost $10 to manufacture, which it theoretically absolutely could, if you fully automate the manufacturing process, well, not the whole assembly, but like it could cost like $100, okay? Most of it could cost 10, yeah. If it costs $10, you'll just buy one every day. You'll just like wherever you are at 8 p.m., you'll just buy it. In fact, if in the future, manufacturing was so inexpensive, that like you could make like an assembly like the one I'm talking about for $10, you would just have an Optimus robot and a software program that automatically buys your design every day and assembles it the next day. So that whatever is wrong with the design, you immediately know the morning after, right? But in the real world, you could have a mistake in your design that you might find out, if you're good, a month after you made it or a week after you made it. If you're really good, maybe a day, but in a lot of cases, like 6 months. And that's because if the design corresponds to a machine that costs $50,000, $200,000, or in old aerospace, like $5 million to make, you're not going to make a lot of them. And instead, what you're going to do is like analyze the shit out of it and evaluate. You're just going to be extremely careful and extremely slow at the design stage. And so what I would say is like, this is kind of a cop-out answer because it's not one specific big technical hurdle. The biggest technical hurdle broadly is that the ability to fabricate the things that we design is not next to free. And if it was next to free, which I totally think it will be in 5, 6, or 7 years, the rate at which we could iterate would be at least double, maybe triple. The cost of our goods would be maybe 50% better, and we'd be a heck of a lot cheaper at developing new technologies if we can manufacture them quickly at scale.
You've been very clear and thoughtful about trying to make it so your iteration loops are super, super tight. And you're also just trying to go through iterations, make the robot in the first place, see what went wrong, see what we need to improve, do it again, and then just run through those iteration loops. How did you kind of come to that philosophy? And then what are you doing to, as the company scales, keep that sort of same philosophy?
Two great questions. So I would say that, we are not the inventor of the idea that iterating fast makes your end product better, cheaper, more quickly. There are probably 20 amazing companies out there that can be pointed to as the source of inspiration for this being a good idea. And now maybe 200, right? If you count the new companies that do the same thing. So we by no means are the proprietor of this idea. We are just astute observers in looking at the fact that the companies with the highest market cap, the best products, the most talented engineers, the best ability to hire those engineers, the most compelling products, I don't know if I said that already, are the ones that iterate quickly. And you could name some names. What we do, and the second part of your question is also super important, which is okay, when you grow, how do you make sure that 100-person org can also turn, a design once every week or once every 2 weeks if needed? The answer lies mostly in making sure that the responsibility of your engineer is really clearly defined. If it's the case, for example, and this is the case at a lot of companies, that you have a product, the product has a product manager, and the team has 6 people or whatever number of people, doesn't really matter. And each, for each person on the team, one person has their hand in a thing, right? Then to go fabricate that item and test it out, you now sort of need the either implicit or explicit approval of 7 people. If instead what you do, and this is the model that a lot of, in my opinion, really great companies use, if instead what you do is you say, okay, I have a growing team, yes, but I'm not going to put more people on one thing. I will just make sure that the scope that each person is working on shrinks and the expected quality grows. Then it can be the case that okay, even though there's a 700-person team, this motor assembly or this, hinge assembly or this computer or this camera is actually the delivery of that product is only up to just one person. And if that one person is responsible for delivering it and is equipped with the money and the tools and the in-house machining and the in-house production to prototype fabricate that part quickly, then your iteration speed will be exactly the same. And then the second component is culture, which is okay, well, does your team like 3 months as an iteration cycle, or does your team care about making the iteration cycle as small as possible? And both of those things are important for us.
How big is your team, by the way, now?
The team's about 16 people.
16?
We're growing as fast as we can find good people.
Yeah.
So if you're watching this, please apply.
Yeah. And how old is the company? Is it 4 years old?
Yeah, the company's about 3.5 years old. We started out super small, just the founders. Like I said, in effectively a garage in San Francisco. I mean, it was a really, really, really shitty place, a rattly garage door. Every time someone drives by, it's super loud. And the basic thing for Starpath is we want to be ready to launch a huge amount of payload to Mars that can produce on the order of low megawatts of power, which roughly speaking is enough for a civilization of a few hundred people, right when the rocket's ready. And so when we started the company, we thought that date was in 2 years.
Yeah.
We were wrong.
Was that actually positive that you were wrong? And because you had an extra few years, that was easier to basically work out kinks and stuff?
I mean, I would say it's neither. We've just calibrated the growth rate of the company according to when we think the rocket's going to be ready. It's sort of like a moving target. And from our standpoint, it's way better to do that than it is to start developing the technology when we're certain that the rocket will be ready, because at that point we'll be too late. The real value of Starpath as measured to humanity is the date that a self-sustaining city on Mars forms
like can happen.
Yeah.
And then like
With or
making
without
that as,
Starpath.
yeah.
So without Starpath, you might say like, okay, well, it'll happen at some date. Our goal is to make that as soon as possible. To say that we think it can be done in 10 years would be, I think, a bit ambitious. You can get a long ways in 10 years. And so waiting an extra, for context, for those watching, you can only fly to Mars once every 2 years. So there's a window in 2026, there's a window in 28, in 2030, in 2032. Well, the 2032 one spills over in 2033, but you get the gist. And so waiting, basically missing a window is missing.
Huge deal.
It's a huge deal. It's missing 2 years where during those 2 years, you could have, let's say, launched a mission, gathered data, used the data to fix or improve the products, and then scale production of those products for like a 10x bigger deployment the following year. So it's like, if you wait 2 years, you could conceivably be 10 times behind where you want to be. If your plan, which ours is to grow 10 times window over window for the first few windows. So in 2030, we could be where we would be, in 2028.
Hypothetically, if 2024 had happened.
Yeah, exactly. So it's like you don't want to miss a window. So from our standpoint, we're basically just like, a cheetah hunting its prey, where the prey is the rocket launch and we are the cheetah, and the movement of the cheetah represents technology. It's kind of a bad analogy, but
yeah,
we're tracking a moving target. So when we started the company 3.5 years ago, we thought, okay, we're gonna be launching super soon. There have been some benefits in going slower, but my
you would have liked it to.
I would have liked it to be faster, which everybody would have. I also will say that our opportunity, like the opportunity for making a really, really, really big splash on the first Mars window, is there now. It wouldn't have been the case if the rocket launched sooner, because we wouldn't have been able to build as much.
Has SpaceX said publicly how many Starships they're trying to launch on the first mission?
Yeah, so Elon has said publicly, and like I said, I'm not a spokesperson for SpaceX, so like reference their website. Elon has said publicly that they want to send a few test ships to Mars in 2026, which I'm optimistic about.
And a few is like 3 or 10?
I don't know if there's a number. I think like 5 or something.
Hopefully it's enough. Yeah.
Hopefully it's enough, but no cargo. So just like try to get the ship to land. It's extremely challenging problem to get a ship to land on Mars. It's like hitting a bullet that's moving, where like the bullet is like the size of it's extremely small in the context of how far you're traveling. So it's very challenging. We've done it before. We've also missed before. Like Mars missions in the past do not have 100% success rate of even hitting the planet Mars. Yeah.
And what do you know what went into the misses? Like why that happened?
Yeah. It's so straightforward. So basically, when you're trying to get to Mars, what you're doing is you're slingshotting around the sun, and you're slingshotting around the sun to try to catch Mars on the other side of the sun from where you launch. So if you launch, let's say this is the sun, and Earth is moving around like this, and Mars is moving around in a bigger circle. We'll just call them circles for simplicity. When you go to Mars, what you're trying to do is slingshot around the sun to catch Mars halfway around the other side of the sun. So like roughly speaking, I mean, this is not exactly true, but like if you leave in the summer, you'll get there in the winter. It's really not true, but for simplicity, we'll say that it's true. And if you make your curve ever so slightly wrong, you will not only will you
overshoot it,
you'll overshoot or undershoot.
Insane. Yeah.
And that distance can be so big that, maybe you get in Mars,
like millions of miles.
Influence. Yeah. It could be like a few 100,000 miles. And if you miss, you could like slingshot around Mars, which would be terrible if there was crew on board, because they would be certified dead. It's a grim take, and, I'm optimistic about developing technology that makes sure that doesn't happen. But, or if you undershoot, you may sort of wrap around Mars and actually leave, go out of the solar system. So there's like a lot of ways you can miss, and the only way that you can't miss is if you hit the atmosphere. Because once you hit the atmosphere, then you can use aerodynamic controls and land. Not like an airplane, but the atmosphere can be gripped. At least. The atmosphere can be gripped, so to speak, and you can land. So 2026, SpaceX wants to send experimental vehicles, and I'm really hopeful that they succeed. There's been some recent successes that are really awesome. And then in 2028, SpaceX says that they want to send, an even larger fleet of experimental vehicles. And then in 2030, they're saying they want to launch a large fleet of vehicles. And this is all public information, by the way. So you can look this up and find this information. But
Elon's been very clear that he really wants to basically scale the number of Starships heading to Mars, like maybe even by more than an order of magnitude every single time. Because that's the only way. Like I think he said something like it needs to be over 1,000 Starships going in order to make life multi-planetary and like a self-sustaining city. Yeah,
so we can just work out the math roughly live. The approximate number of tons that you need to get to the surface of Mars from Earth to make a city that's self-sustaining is about 1 million. There's like some debate that number might be 100,000 or 10 million or whatever, but nobody thinks it's like...
You don't want to undershoot.
You don't want to undershoot, first of all, and nobody thinks it's like drastically different. So 1 million tons to the surface of Mars is what it takes to make life multiplanetary, roughly speaking, if you want it to be permanent. Like, okay, the city will not die even if the ships stop coming from Earth for any reason. Each Starship can carry thereabouts 100 tons to the surface of Mars per flight. So what this means is that you need to have, if you had a fleet of 1,000 that could carry 100 tons each, you can now carry 100,000 tons per fleet trip, meaning each time the fleet goes and comes from Mars. And then if the fleet makes 10 trips, then 10 trips of a fleet of 1,000 ships will be
1 million tons.
1 million tons, which is a self-sustaining city. I actually have some optimism that number will actually be a lot bigger. Mm-hmm. I mean, Starpath's business, of course, is not modeled around, there being a 10,000 or 100,000 size fleet of Starships. But I do have some optimism that it might either be a bigger fleet in number or a bigger fleet in terms of the size per ship. Because, it's my opinion that like once you have a business that works on Mars, like once you have the cost of transport below the threshold price that people want to pay, that 1 million ton city roughly correlates to 1 million people. I think you could sell way more than 1 million people on going to Mars.
Especially if it's only like, you have a minimum, you have to stay there for, let's say, like 4 to 6 years, and then you can come home if you want, or like some number of people can come home at that point.
Right. I mean, first of all, I'd say like you probably want to make sure that your supply of transit from Mars back to Earth is bigger than your demand. Like the last thing you want is for people to feel trapped, because nobody will go somewhere that they think they'll feel trapped. So you always want to make sure that the ships coming from Mars back to Earth, when there's crew on Mars, are greater than the number of people that, like, you should have empty seats. Yeah. Obviously from a business standpoint, you don't want to have empty seats.
You just want to basically like fill it with cargo or something.
Fill it with cargo. Yeah. You don't want to have it be the case that somebody who wants to do something can't, because now you go from the greatest adventure of all time to like
the greatest prison of all time.
Yeah, the greatest prison of all time, which like it's our responsibility as humans, as friends of each other, to not imprison our friends. Okay, so relatively straightforward. But going back to my comment on scale, like, I totally understand Elon's take that, okay, you want to have 1 million people to have a self-sustaining city, and roughly speaking, agree with it. That being said, when airplanes were made, people said, okay, airplanes are extremely costly, and they're going to be used in these niche circumstances where like you really need to get from one place to another, or maybe have a lot of money. And now airplanes are less expensive, energy is a little bit cheaper.
I think I forgot exactly how many, but it's like over 100 million annual passengers or more than that.
Yeah, so there's hundreds of millions of passengers per year. Now, obviously, flying on an airplane is very different than flying to Mars. But my basic point here is just that it's very hard to predict. Like 1 million is a number that's based on what's required to make life multiplanetary. But if you think about it from a business and demand standpoint, if you shoot for 1 million, you're actually way more likely to overshoot than undershoot, because 1 million means that you've built a compelling product that is broadly liked by people who buy it. And so if a product is broadly liked by people who buy it, you make it better over time. There's no reason why you couldn't sell, 10. I think 100 is probably your limit, where it's like, okay, at 100 million people, you're now looking at a meaningful portion of the species, right? Like over 1%. So like, I have like, hopeful aspiration. I'd say I'm cautiously optimistic that the future actually has way more than 1,000 Starship-sized vehicles, or maybe 1,000, but they're way bigger.
Yeah, and like by future, you mean like near term? I would assume that eventually you'd want like tens of thousands every launch window.
I mean,
there's really like no reason to not have an insane amount.
It's super challenging. Yeah, by near term, I mean like 20 years. It's super challenging to predict like what happens in 20 years. If I could predict what happens in 20 years, I would just go to I would go to Polymarket and just become a billionaire. As in, I would just make some bets on high 0.00001% probability, and then like pay off 10,000 to 1 sort of thing. So it's hard to predict, but from first principle standpoint, it's like what the challenge we're looking at is, okay, how do we make a product which is transit to Mars, including obviously return journey, what you do when you're there, and everything in between, food, water, everything, that's so compelling that people actually want to buy it. And obviously we're starting by building the thing that's the most important, which is the propellant production plant. But when you look at that problem, it's not obvious that you couldn't solve it. You couldn't close that for 5 or 10 or 20 million people. Mm-hmm. there's if you could close 100,000, there's no reason you couldn't close 10 million. So I'm definitely optimistic that it'll be more. Time will tell.
Ironically, like on making Starship rapidly reusable and like going from Mars to Earth, it seems like the propellant is a huge deal. But then actually, if it takes like 95% of the energy that's going to be used on Mars just in the propellant making process, the hugest big thing is just making enough energy. And so for you on making solar panels, how are you thinking about like really ramping the scale of manufacturing these solar panels so that you can kind of make all that energy?
Yeah. Okay. So a totally correct input assumption that you need to make a shit ton of energy on Mars to make a city there. The approximate number is about 100 kilowatts per person. It's like 10 to 100 kilowatts per person.
And can you put that in like context? Like
the average house is like 2 to 5, maybe sometimes 10 kilowatts. Like a big house with air conditioning is 10 kilowatts. Small house with no air conditioning is like 2 kilowatts. When I was growing up, my house pulled an average of 1.3. That's because my family's like super interested in.
So it's going to be like 50 to 70 times average consumption on Earth on Mars.
Yeah, but I gave you the per household number on Mars, and I gave you on Earth and the per person number on Mars. So it's actually more like 200 times.
200 times.
So you need like 200 times the power per person, because most of that energy is spent on powering the plant that makes the fuel for that person that they will eventually use when they go home. And I mean, the rockets are like the size of a swimming pool. Yeah. So you're talking about like swimming in rocket propellant, just to give you a sense of scale.
You need to make a lot of rocket propellant.
Yes, exactly. So going back to your question, how do you plan on scaling solar power production? You're definitely right on the input that you need to make a lot of energy. And that's by the way, the key, like sort of just for context for those listening, Starpath just announced a commercially available solar product for satellite companies. So we make our own solar panels now. And if you're a satellite company, you can buy them for about 1/10 of the cost that they could be otherwise purchased from existing vendors. We did not intend to enter this marketplace, but the reason we entered this marketplace is because of what you're saying, which is that we needed an extremely scalable.
The biggest constraint.
Yeah, it's one of the biggest constraints. I mean, I would say technology is the biggest constraint, but from a manufacturing standpoint, the good that we need to produce the sheer biggest quantity of, measured in count, is solar cells. We need like 100 million solar cells on the surface of Mars to make even a moderately sized city.
Let's actually put that into context as well. How many solar cells do we have on Earth?
Oh boy, I actually don't know the answer to that question.
But a lot.
Okay, so the approximate the unit of measurement for solar on Earth is watts, and I believe that the total production of solar modules in the U.S. is on the order of about 10 gigawatts per year. I could be wrong. Okay, don't quote me on that. The total production of solar modules for, this is a better question, all space applications combined is about 40 megawatts, 50 megawatts. So about 50 million watts is all of the power that's used on every spacecraft launched from Earth today, out of which the majority of that is Starlink. And that's like a rough number. You might as well just call it 100.
I mean, I think Starlink is already like over 90% of all satellites in orbit, right?
Yeah, so Starlink's majority, obviously they account for the majority of the power. But just to give you a sense of scale, all spacecraft that orbit Earth, every year, the spacecraft that are manufactured, it takes about 40 million watts of solar panels to power those. For Mars, you want to have, you're not going to believe me, about 40 gigawatts of total power. 40 gigawatts. So 1,000 times more power. Now, out of that 40 gigawatts, we'll probably produce about 4 using solar energy. So
4.
Yeah, 4. So about 1/10. So about 100 times more power than all of satellites combined.
Yeah.
And then past 4 gigawatts, there's roughly speaking a threshold at around, it's actually less than 4 gigawatts, but there's a threshold around 1 gigawatt where it becomes more cost effective to develop a nuclear reactor. And so early on, we'll power Mars using solar cells, and that's the product that we produce in the biggest single quantity today. It's not necessarily the most important product we build. I would say that that's probably not true, but it's the product that we produce in the biggest scale. And we have a mostly automated production line that makes those cells at a pretty magnificent rate. So we can make millions of watts per year today. And in the future, we're going to scale that all the way up to maybe 400 or 500 megawatts. And then at that sort of 400 or 500 megawatts per year production rate, we'll level it out. And the remainder of the growth for the city on Mars will actually be powered by nuclear. And that's because nuclear gives you a couple beneficial traits. The first is that your total power produced per mass is a little bit better. So you're able to cram more power onto a rocket, which as you're trying to scale the power up a lot, you're going to want.
Are you talking about like just shipping uranium, basically?
Exactly.
Yeah.
So if you just ship, well, you would ship early on a complete nuclear reactor. But that
It's
could
also fucking nuts that you can ship a nuclear reactor on Starships.
Well, to be clear, you can't yet. Like there's a huge regulatory there's a huge regulatory, burden. It's also the technology doesn't exist yet. So there doesn't exist, for example, a 10 megawatt nuclear reactor I can buy today, which I would if I could, and then put it on a Starship.
Like the small modular doesn't exist yet.
Yeah, I mean, people are making it. There are a lot of great companies actually in this area that are working on nuclear reactors, some for space. And so that technology will come around. It's unclear yet whether Starpath will be in the manufacturing business of that product or the buying business of that product. But the advantage of solar in the early days, the reason why we use it is because the cost and schedule are better. The cost to get a solar panel that works is extremely low compared to a nuclear reactor. And we can do it today. In fact, we've done it today. There are no rules that say you cannot launch a solar panel to space. In fact, a solar panel is launched to space 4 times a week on a Falcon 9. Every Starlink satellite has a solar panel. Every satellite that goes to space has a solar panel. So
are they launching 4 times a week now?
Something like that. It might be like 3 times a week. So maybe I'm exaggerating, but yeah, they're about like between 100 and 200 Falcon 9 launches.
It's very
per year.
like proven. Like this is a known thing. People do it all the time.
Extremely known. Yeah. So how do we scale? Well, the production is automated. Automated production is easy to scale. You just buy more lines. So if you have a line that produces some amount and you want to make 10 times, you just buy 10 lines.
You just Factorio it and just basically copy paste.
Exactly. You Factorio the production of solar panels, which is something that we're actively working on right now. And in the long term, you'll Factorio the production of nuclear reactors. And, there's some great companies out there that I recommend you look at that are working on that for Earth applications. Scaling the production of solar panels is actually not the most challenging thing in the world. The more challenging part, which is the problem that we're solving today, is dialing in one production line, or in our case, 2, that can make solar panels well. And then once you have a production line that works, copy and pasting it, like you said, Factorio style, is not the challenge. There's some
just making the first one is the
making the first one's the hard part, and we're mostly there.
Ironically, I think Elon basically says like prototyping is easy, production is hard. So you're kind of thinking that actually it's just going to be prototyping is hard, production is going to be relatively easy relative to that.
Well, I mean, I would call the creation of one production line production. And that is hard. Yeah. And that is hard. So I would agree with Elon that production is hard, prototyping is easy. You want to make one solar panel with your hands.
That's a pretty doable thing.
It's doable. It's a pain in the ass. I wouldn't recommend it, but it's doable. And then, if you want to make 1 million, you need a machine.
Yep. Okay. So what do you think the biggest risks are for your business? Like making it actually work?
Yeah. I mean, there are like sort of 2 categories of risk. And I basically price one of those as 0 and the other one as being a challenge, like a sort of a combined challenge of both. So the first challenge is that, can you make technology that works? And I price this at 0 because, as in 0 risk, because even if you can't make technology that works, it's just a question of how many tries you need. We think it'll take us 2 or 3 tries. We could be wrong. And even if we're wrong, the business will still work. Okay, so that's one category of risk. The second category of risk, which I think is far more important to understand and evaluate, is, okay, the business explodes. It's worth $50, $100 billion or more. If people want to go to Mars and you've built a product, which is a transportation service, a return service, and housing, et cetera, when you're there, that's compelling enough that people want to pay for it. And this is a much more important question to ask, because it really will lead you down the path of developing the correct technologies that people will want to actually buy. The biggest risk of them all is that even if you make a fully and rapidly reusable rocket, a low-cost rocket propellant production plant, a habitat that's beautiful and delightful to live in, and a food production system that makes delicious food, and all of the other things that would make the best case outcome for everything.
It sort of a Garden of Eden sort of situation.
The biggest risk for Starpath is that even if you do that, the value proposition to customers to travel to Mars for $100, $200, $300, $400,000 in the long term, okay, the prices early on will not be that, is not a good enough value proposition to convince people to go. And if that's the case, then Starpath won't work, but that is not a reason not to try. right? Like this, like to say I'm not going to try to build a city on Mars because I don't think people will like it is like the equivalent of saying, I will not build, abundant electricity because I don't think that the power needs should go up.
I think the first pitch for people going to Mars is roughly similar to like, do you want to be a Navy SEAL, and like, do you want to go through that program to try to prove that you are like the best and push yourself to the limits, sort of situation.
Well, I mean, I think the Navy SEALs are incredible. So I wouldn't say that like I would, if I was going to Mars, I would not compare myself to a Navy SEAL. I would put a Navy SEAL above me. But I think the pitch is similar to that, which is like, do you want to embark on what is almost certainly to date the greatest adventure that any human has ever done, despite for millennia humans dreaming about an adventure as epic as this? Do you want to do that? And I think we can get, for the first few ships of hundreds or thousands, not hundreds of thousands, but hundreds or thousands of people, like that pitch will work. And so I'm completely not worried about the first 10 ships or the first 100 ships. What I'm worried about is how do we make a product that is so compelling in 7 years' time, where once you're past, or 8 years' time, or 10 years' time, where once you're past that initial few ships, I say few, it's still like a lot, but once the product goes from completely novel to less novel, how do you still make it the case that people want to go to Mars for the prices that you can sell a round trip ticket to them for?
Yep.
I think the novelty will stick around for a while.
I don't know if it would ever go away. Honestly, like I
hope you're right. I hope you're right.
I think. Well, I think for even if you said only novelty for the first 1 million people to go to Mars, that's still how many, in perspective of number of humans alive. That's like
it's like under
0.001%.
It's under 0.1%.
Yeah, exactly. And I think it will be a novelty.
No, it's actually it's just over a tenth. No, it's under 10%. My mistake.
Yeah.
It's not clear. It's not clear to me. But from our perspective, it's very simple. It's like, okay, start with the basics that matter the most: energy production, propellant production, which, by the way, we haven't talked about this yet, but propellant production also implies the production of water and oxygen for drinking and breathing. So it's like, because
that's just part of the process.
Yeah, it's just part of the process. So like oxygen as a liquid is fuel for a rocket. If you turn a tiny bit of that into gas, you now have oxygen for breathing. And then, of course, we talked about how water is a pre-product of oxygen. So if you just take a little bit of water out of the system before you turn it into oxygen,
that's for humans.
That's for humans to drink. It's a negligible quantity. Like, you will not outdrink a rocket engine.
Yeah. So in the process of making the rocket fuel, you basically make way more water than you could ever need for humans.
Yeah. So what we say, the sort of like line that we repeat is, by creating a rocket propellant production plant, you create a virtually unlimited supply of water for drinking and oxygen for breathing. Basically, like, use as much damn oxygen as you want. You can have a leak. I mean, you'd have other problems if you had a leak in your habitat, but from a production standpoint, you could have a leak in your habitat and it wouldn't be a big deal. But yeah, from our standpoint, it's simple. It's like, okay, start with the basics, things that matter the most: prop production, life support, power. From there, 4 years, 6 years down the road, start answering the question of, how do I make sure that this business continues to have a compelling product offering in the worst case that the novelty does wear off? Like, okay, you and I hope the novelty never wears off. People are eager to go once they realize it's accessible and it's safe.
And they're not going to die.
Right. There'll be some people who are
once you can get over the hurdle of you're probably not going to die on takeoff or landing.
Yeah. So like, I would be willing to go even if I was going to possibly die.
What percentage?
About
probability?
20%.
You'd go 1 in 5 or 1 in
I die 1 in 5 times.
Wait, 1 in 5. Well, that would be 20%.
Yeah.
That would be, wait, really? 20% chance?
Yeah. So 20% is my threshold for going. Like, if I was 50-50 likely to die, I think I would say, let's send some robotic
I don't think
missions.
I would do 20%. I think I would probably do like 0.01%.
Yeah, like an airplane. Zero, basically.
Well, no. I think an airplane is like once every 12 million passengers.
Yeah, airplane's like extremely good.
Yeah, it's insanely good.
I think we don't necessarily want to be selling the public on this like 1 in 5 chance of death. I'm just saying, like, my threshold is 1 in 5. For me personally, I don't expect that to scale. And, I think we should aim for a safety of like 100% safety, or 99, like, we should aim for basically zero. There will be some, okay, like, practically speaking, you can't say like, I'm going to colonize a planet and then nobody dies ever. There'll be some mistakes, but I think we should aim for a safety that's like, I think airplanes good. good
Airplane's
benchmark.
good safety
It's
measure.
a good benchmark. Like, yeah, everyone goes on airplanes. Nobody cares about it.
I think the really important thing is basically you, and I think Elon's very conscious of this. You can't set a precedent for the first Starship that goes to Mars with humans on it blows up, because if that happened, that would be horrible for the mission.
Right. Yeah. I mean, if you look back at Demo 2, which was Dragon's first flight, there's I think there's a documentary about it at this point, but basically like the opinion that the SpaceX team had at the time, according to, what you can find online, is like, okay, whatever we need to do to make sure that the rocket doesn't blow up, we're going to do that. So that's a great safety posture for the first few missions. And then after the first few missions, hopefully maybe you only do your risky stuff on missions with no humans on it.
Yeah. Optimus is on board.
Yeah. Optimus is on board, or our robots on board. And, we say this all the time. It's like our technology, like, because we've taken the idiot index of production so low, is low cost of manufacturing enough that it's completely fine for us to take some risk that the rocket blows up. Like in the normal aerospace world, like if you're a satellite customer, like your satellite costs so much money that if you're the rocket company and you blow up the satellite, it's like a nightmare. Like you have to get insurance. The insurance costs a lot because of course there's big risk and the payout's huge. But for us, it's like we want to build equipment that's effectively commodity, at least for us to produce, to the point where, if you blow up like 1 in 10 robotic missions, like, we don't care. I want to be very clear. I'm not suggesting you should blow up 1 in 10 human missions. I think you should blow up 0 in 10 human missions. But for a robotic mission, 1 in 10 blowing up, no problem. Even 1 in 3 blowing up is no problem. That's just a 33%, or 50% overhead in terms of building 50% extra stuff.
Yep.
It's like no big deal.
So I know when Airbnb started, I think Brian, Joe, and Nate basically didn't hire anyone for, I think it was like the first 2 years, and they basically just built the company. Were extremely conscious about not hiring the wrong type of people, and they were very focused. I think at the beginning, Brian had this line where he would ask someone, if you knew that you were going to die in 10 years, would you still, what would you want to do? Would you still be wanting to work on this company, or would you go do something else? If something else, then probably go do that. How, I know you said you basically have 16 people now, and you're very conscious about how you're hiring. How have you kind of found people that are very aligned with the mission and are excited about this kind of future that you're trying to build?
Yeah, I mean, I would love to give you some magic bullet answer.
Mm-hmm.
The short answer is just not hiring a lot of people we interview. It's tough.
What's the biggest reason that you don't hire someone?
The biggest reason we don't hire someone is we don't think that, basically we don't think they have the mission alignment we want. We want people who work at Starpath to look at the problem we're solving and go, holy shit, this is the next big thing. And we want people who work at Starpath to read about how the technology we built is quote unquote impossible, which is commonplace for us to find on the internet, that it's something that we've done in the real world is quote unquote impossible in the eyes of someone else, and be like, yeah, whatever, it doesn't matter to me. We're
going to keep on doing it.
Yeah, we're just going to keep on doing it. And so, we find tons of smart people, tons of people who are extremely good at, the things that we want them to do. And we still make tough choices, which is to not hire some people, even if they're really good, because we want extreme mission alignment. Okay, but you asked it sort of an implicit question under there, which is if I found out that I was dying in 10 years, what would I do? And when you were talking about it, it got me thinking. And I think the answer is, if I knew that I was going to personally die in 2035, okay, so that leaves the Mars 28 window, 2030, 2032, and 2033.
2034, I think, right? Or no? Oh, yeah.
No. It'd be 2035. Yeah. So if I was going to die, okay, 4 or 5 Mars windows, I think we would stick to a similar plan for the next year and a half, 2 years, which is to get equipment onto the surface of the moon for testing, to be confident that the machines we're going to produce at that scale actually work. And then as soon as we have confidence for any particular machine, just do whatever is needed to finance the living shit out of it and make tens of thousands of units and store them in a warehouse. That's what I would do. It's just okay, well, we know the machine. It's not like making a city on Mars is this super complicated thing where we don't know what the implementation is. We know the implementation. It's make robot that produces power, water, oxygen, and then a long trailing list of other stuff. We know how to make the robot that does the robots that do the bulk of that. So if I was going to die in 10 years, I would just do everything I can to make as many of those robots before I die. So like maybe you only need 100,000 to make a city on Mars. Just make all 100,000 right now. Which, by the way, in automotive terms, is small numbers. Like it's very normal for a car to make 100,000 units a year. It's like, in fact, low. Like
that would be a very bad car.
Yeah, a shitty car would
be like I think Ferrari does really low production on a few models and stuff.
But yeah, like a Model 3, I don't know the numbers, but I think it's like
millions.
It's like 1 million or something.
Well, and they want to scale it to, or at least, whatever the autonomous vehicle is, it's going to be like 20 plus million a year or something like that.
Well, those are crazy numbers and I hope they achieve them. But my point is just like 100,000 robots is like small fish in the game of robots at scale, which automotive is the best example of robots at scale.
I love this Jeff Bezos, like the regret minimization framework, where he basically says like project himself out to age 80 and look back and say like, what would I have regretted if I didn't do? Like, what actions would I regret not taking? What are those actions for you?
It's hard to answer without just saying like what I'm doing now. I would say at least on that list. Okay, so obviously on that list is doing whatever we can to build the city. Definitely also on that list is doing whatever I can personally after we finish developing the technology to go live in the city. Like one of the things I talk to my parents about sometimes is like, once we're done making the technology here, I kind of want to just go do like, I don't know if this is like PC, but like a bit of like slave labor. Like I want to just go to Mars and just like do the shittiest few jobs.
Grunt work.
Yeah, just grunt work. Like, because at the end of the day, like, numbers on a screen going up are important for businesses, but they don't feel the same as like, the type of stuff you do as a kid, which is like build a fort with your friends. And so like, I want to do like the shitty manual labor on Mars so that I can feel like the whole spectrum of satisfaction.
The equivalent of working at McDonald's on Mars.
Oh, for sure. Yeah, 100%. Like if McDonald's has a Mars, dude, if McDonald's has a Mars, think about how fun it is. Like, okay, at McDonald's on Earth, you're like frying fries, which is like not that interesting. But the equivalent of Mars, okay, well, for some it's interesting. I used to work at a burger store when I was younger. It's called Five Guys. It's like, I love frying fries. Yeah. I actually love cutting the fries, but we don't need to get too far into that. It's really fun. Like the equivalent of cutting potatoes on Mars will be like repairing the cutting teeth for a mining robot, where like each tooth that you repair corresponds to like, 7 tons of mined material. So like, just imagine how like rewarding that is to like sharpen a tooth, put it in a bucket and be like, dude, this bucket represents like the oxygen production for like 75 people, that would die without these teeth. or like, like you hypothesize, like, what do you think the like, yeah, just like, what do you think the manual labor jobs on Mars will be? Obviously, most of it will be automated, but a couple things here and there will still be manual labor.
We need like labor jobs for 100 to 1 million people, 100,000 to 1 million people sort of situation.
Yeah. So I would just want to go to Mars. So my bucket list for minimizing regret is to go to Mars and do one of those things. And then maybe like, if possible, like if easy, get on a spaceship and like visit Jupiter or something. Not the planet, just orbit. Obviously, you land on Jupiter, you're dead as a doorknob. But I'd like to maybe go see some of the gas giants up close. I mean, there's some pictures we have that are like sort of like dynamic super resolution, where like we have shitty pictures and we've like made them better using After Effects and whatnot, that are so cool, like various cloud patterns and storm patterns on Jupiter. So maybe I'd want to go see those, but it's like from a feasibility standpoint, it might be like, well, a lot of money, but definitely going to Mars and doing some labor is on the list. And past that, I don't have much on my bucket list.
Isaiah from Valor talked about the idiot index in the nuclear reactor industry being like 140 to 1 or more. What is the idiot index for space, and how are you kind of like lowering that?
Yeah. It's hard to say, but it's at least 100 to 1. Mm-hmm. And 100 to 1 is sort of like past a threshold that you and I were talking about today that, I won't name, it's like, it's past a threshold where you definitely, there's no excuse for 100 to 1 idiot index.
We talked about before this started, we talked about the retard index, which is
not endorsed by me.
If you're, that's just me. But if you're above 60 to 1 idiot, do you want to explain what the idiot index is for people to understand?
Okay. For those who are listening, the idiot index is a index that can be defined for any finished good, which is the ratio of the cost of the finished good, so maybe your iPhone's $1,000, to the cost of the
Raw inputs.
raw inputs. Now,
Like the
practically, you want to define the idiot index where the numerator, the finished good product, is the price that you pay, and the denominator is the price of all of the commoditized inputs. So you don't want to call like a chip 1 cent because like technically it's 1 cent of silicon. You want to say like, okay, the chip is like $2 because that's the lowest you can. That's a commoditized good, and we already know that you really can't get a chip below $2, at least for now. And in aerospace, the idiot index can be like hundreds or sometimes thousands to one, where like you buy a product, and we buy products like this all the time for early missions where, we haven't yet vertically integrated it, where like the product might be like $10,000, where if you had the design for the product, you could fabricate it for 50 or 20, where like the idiot index is like hundreds and hundreds to one. And the idiot index is a good sort of gut check as to whether or not the finished good has like, if is a good deal. And if you're basing some sort of economic model or constraint against the price of an item, you also want to know the idiot index. Like you don't want to say something like, oh, it's impossible to build a city on Mars because, like NASA's Mars rover cost $1 billion. Well, it's like the idiot index, which, okay, it's hard to call the NASA Mars rover idiotic because it's not. It's like an extremely capable machine. But at the end of the day, it's very expensive to build. And so if you wanted to make 1,000 of them, you would not take the price of making that thing and multiply it by 1,000. You would take the price of that thing, see how much you can improve it, which might be itself 1,000 times, and then multiply it by 1,000.
Go from like 500 million to like 500,000.
Yeah, so NASA could have a robot that costs 500 million. You could make it for 500,000. Actually, ours costs less than 500,000. And then you would multiply that number by 1,000 to see like, okay, what does it cost to make 1,000? And nuclear, the idiot index is super high, mostly because of this is like the big irony, mostly because of
Regulatory.
Yeah, it's not just like that's only half the irony. It's mostly because of regulatory, and furthermore, the majority of the regulatory burden in making nuclear reactors comes from people who care about the environment, which is like fate loves irony. Like the nuclear reactors are like one of the best technologies for protecting the environment because you have effectively emission-free energy production, like basically zero emission. Like,
relative to all other forms of energy production.
It's even better. Like it's better than solar. It's better than wind. And I'm a big fan of like every form of energy production in the world, less than probably like coal mining. And it's even better than those. So like nuclear is like the ultimate technology. And regulation makes the idiot index super high. And in aerospace, the idiot index is super high because almost all of the goods are sold at extremely low volume. So like if you've made a thing, it costs $100 to make, but you spent 200 grand making it and you're only going to sell 5. Well,
you got to charge like 100
it's at least 40 grand. And if you want to make a profit, it's going to be 200 grand, right, per unit. And so you're asking about like, okay, what's our experience like buying in the case of solar panels from, existing vendors? I don't know what their profit margins are, but all I can say is that because they're
only selling to a few satellites every year.
They're only selling to a few satellites every year. They have no incentive to make the price small. And when the price is like $1,000 a watt, where on Earth we make solar panels for like 44 cents per watt. Okay, you can go to Home Depot and buy a panel for like under $1 a watt. The incentive to make the production cheap isn't really there. And so the idiot index is super high, and more or less like the first order of magnitude improvement you can make on the idiot index for any given good in aerospace is by just trying to make it cheaper. Like if all you do is you ask like, okay, what are the expensive parts? Like what are the parts of this that make it expensive? Is it labor? Is it like a unique material that there's only one supplier of? Is it like a finished good from another company that has a high idiot index? And you just remove that, you'll usually get a 10x improvement. So if all you want is 10x better, all you got to do is like for most applications is just look at the thing, ask why it's expensive, find the thing that costs the most, which usually accounts for 90% of the cost, and remove it in one way or another. Maybe you remove it by like testing a cheaper alternative and it works. Maybe you remove it by integrating the production, like vertically integrating the production of that costly good that's making expensive, or some other creative solution. And this is like, I won't speak for other companies, but this is like roughly speaking how like all of the products that have seen scale in the space industry, of which there are a few, have reached that. Just like, okay, what's expensive? Okay, delete that, add something else that's, maybe like 20% worse and 1,000 times cheaper. In some cases better and cheaper too. And And basically we do the same thing. Now, in some cases, you want to make like a more than 10x improvement. Maybe in the case of rovers, it's like, okay, 100x improvement, whatever. And so in that circumstance, you sometimes have to take like a completely different approach. Like, okay, maybe the reason why this is expensive is because you have a requirement that isn't real. Maybe it's the case that you think you need, fault tolerance or redundancy, but actually, if you work out the economic model and you say like, okay, 90% or like 10% of my machines will fail completely, that's actually much cheaper than, making it so darn reliable that only 1% of your machines fail. And so it's like sometimes those are like, tricks you can use to make your cost basis way lower. But it's pretty case by case. And actually the first thing gets you like most of the way there. Like if you just ask like, okay, why is this motor $40,000? Which is like you can shop for motors online for spacecraft that are $40,000. Like easily you can find that. And you just ask yourself like, okay, which step of making this motor like costs 40 grand or 20 grand? And either just delete the motor entirely and make a new one or something in between. You can get like usually from 40,000 to 4 pretty easily.